Thank you very much for your time once again. We're continuing our conversations on the some important laws and theorems of probability. And in this particular session, we want to consider the idea, a very important concept for that matter, on how to evaluate certain probabilities, given that there have been some a prioris. In other words, how do we evaluate the probability of a particular event, knowing or giving that some other event has taken place? All right. An important difference between just computing, for example, the probability that the rains would fall today versus computing the probability that the rains would come down today, given that the rains came down last night. Okay, they're very similar in the way they're framed, but there is an important technical difference, an important probabilistic difference. In one case, it's an absolutistic probability that we're finding. In the other case, there is a condition, right? What is the probability that we would observe this particular event, in this particular case, the rains, given that a previous event has taken place, right? So we want to establish the foundations for conditional probabilities, and that we would use that as a lever to sort of build on our discourses on probability. All right. So giving two events in the same sample space, right? The probability assigned to A or that will be assigned to A when it is known that B has already occurred is what we call the conditional probability of A given B. All right. So let's just maybe put down a definition. So a formal definition. So the statement I just made is just like an everyday conversational definition of what conditional probability means, right? So let's look at the actual probabilistic definition. So this is our definition, first definition for the day. So let us consider two events. Two events, right? A and B. Right? And let's impose this. So defined on the same sample space. Then the conditional probability of the event A giving B is, so notationally, we write the probability of event A given B by this. So A, and then we use the pipe B. Right? So the probability of A given B is the probability of the intersection the probability of the prior events. And of course, for this to be defined, it means that the probability is greater than 0. All right. So yes. So just to sort of recap this. So keep in mind that this is the pipe symbol. It's a straight. It's a vertical bar. All right. It's not like a division sign. Right. So this is A and then a straight bar B. Okay, and the conditional probability of A given B is the probability of the intersection of A and B expresses the proportion of the probability of B, right? And this probability of B, of course, has to be greater than 0 so that it's defined. All right. So, I mean, this means that so this is a trivial point, right? So it means that this probability of A given B, all right, is not defined. Is undefined. Okay, if this probability is 0. All right, and this is clear, right? Now let's take a few issues here. Let's look at a few cases. So case 1, right? What happens when A and B are mutually exclusive? Okay, so where A and B are mutually exclusive, all right, where A and B are mutually exclusive, what happens? Then it means that A intersection B obviously is empty, right? And thus, it means that the probability, the conditional probability of A given B is going to be the probability of A intersection B over the probability of what B. And because the probability of A intersection B will be 0, okay, because it's an impossible set, it means that we're going to get 0 over probability of B, right? So this simply means that whenever the conditional probability of A given B I mean, whenever A and B are mutually exclusive, then the conditional probability of A given B would always be 0. Let's take another scenario. So case 2. So where we have this scenario, B being a subset of A. Okay, sub or equal to, potentially equal to A. Then what happens to the conditional probability? So we have the probability of A given B. Right. So let's consider the second case here. Right. So the second case where we have this. All right. Then it means that what happens to the conditional probability? Right. So the prob of A given B is right. Now think about it. If B is contained within or equal to A, right? So B is a sub of A. Then what is the intersection of A and B? The intersection of A and B would definitely be B, okay? Because B is contained within or equal to A. So B will be the smaller set, okay? Even if B is equal to A, the intersection is still a safer choice will be to just say it's B, right? So therefore, the probability of A intersection B now becomes the probability of B. Okay, and this means that whenever you have one event being contained in the other, in this case, if the prior event, when I say the prior event, I mean this, the one that comes after the conditionality or the given by, right? If that reference event or that prior event is contained within the main event, okay, the event of interest, then the conditional probability of the event of interest given the prior event would always be equal to 1. Case 3. Now let's look at the other way around. What if instead of the reference, the prior event being contained in A, now our main event, A, is contained in B. So where A is a subset of B this time around, then It means that the conditional probability of A given B, right? The same definition this time around, A is contained within B. Okay, so it becomes probability of A over the prob of B. All right. So let's take a theorem. So, so let's call this theorem right. So theorem, this is just continuing from the previous series of theorems that we've looked at in the past. So is it theorem 5, theorem 6, they're about. Okay, so let's take this. It says that suppose, or let's consider a finite equiprobable sample space. Right? Equiprobable sample space would mean that all of the events therein have same, probabilities of occurrence. So for example, if you take a die roll, right, or a coin toss, the probabilities are 1/6. I mean, for each event is 1/6 and 1/2 respectively, right? So consider a finite equiprobable sample space with events. With events A and B. Then it holds that, okay, so then the following is true. It holds that the conditional probability of A given B would be the number of elements in A intersection B, okay, over the number of elements in B. And of course, for this to be defined, it means that the number of elements in B would not have to be 0. All right. So once we talk about theorems and laws, they all have to be established, right? So we need to look at the proof for this. Why? What makes this true? We can't just make this claim and leave it at that. Okay, so let's look at the proof. Right. So we know that generally, right, in general, the probability of A intersection B is the is given by this, the number of elements in what A intersection B over what? The number of elements in your sample space. This is just a classical definition of probability, right? Good. So also, or let's say, so we can start by saying that observe that this is true. Okay, and also we can look at the probability of B. The probability of B also similarly is what? The number of elements constituted B over the size of your sample space. All right. Hence, the probability of A given B, which is what we're expecting, is going to be, as we know, the probability of A intersection B over the probability of B. And this is actually the number of elements in A intersection B over the number of elements in omega. All that over the number of elements in B over the number of elements in omega. Okay. And if you simplify this is equal to, this is basic algebra, right? So this just becomes number of elements in A intersection B, all right, on number of elements in the sample space, okay, multiplying number of elements in your sample space over number of elements in B. And this is definitely equal to number of elements in A intersection B over number of elements in B. All right. So we've proved this. So it means that anytime that you want to compute the probability, the conditional probability, okay, of one event given the other, it's essentially the same as just taking the ratio of the number of elements in the intersection to the number of elements in the reference event. All right. Let's take a look at some other issues. So I want us to consider what we call the multiplicative or the multiplication law of probability. All right. So the general multiplication law. Recall that we had what the general addition or the additive law. So we're also looking at the general multiplication law. All right. So theorem. So the numbering of the theorem is supposed to follow from where we left off in the previous meeting, but just for purposes of today, let me just call it theorem one. Or well, I mean, just for consistency's sake. So I'll just leave it at that. So I'll just call it theorem star, and so on and so forth, just so to signal that it's a continuation, right? And the numbering would have to follow in that regard. So this is our second theorem for the day. Okay, so what does this say? All right, so consider two events. Consider two events in, so of course, when I say consider two events, I'm referring to some A and B. So consider some two events, A and B. All right. In okay, in the same sample space. Then the probability of the joint occurrence all right, of A and B is so we're looking at the probability of both A and B happening. So that's just like saying that we're looking at the probability of the intersection. So this is the probability of A intersection B is equal to the probability of B multiplying the probability of A given B. And this is the case if the probability of B, okay, is not equal to 0. Because then otherwise, the whole probability just goes to 0. Okay. And we can also write it in two ways. So this is the first case. So it is also equal to the probability of A multiplying the probability of B giving A. All right. If the probability of this time around A is not 0. Okay, so in other words, the general addition law, I mean the general multiplication law is telling us that we can find the probability of a joint occurrence of two events by taking the product of one event and the alternating conditional, right? The alternating probability of conditional of the other. So in the first case, we can write this as a product of the probability of B multiplying the probability of A given B, right? So keep in mind, whatever you choose, in this case, we're starting with the probability of B. It means that we need to multiply it by the probability of A given B. All right. And if you think about it, just do this small algebra in your mind. We know that the probability of A given B is what? The probability of A intersection B divided by the probability of B, right? So that probability of B cancels this probability of B, and you get back this, right? So in the same way, if you're choosing to go with the probability of A, then it means you need to multiply it by the probability of B given A for the equivalent to hold. All right. So let's try to prove this also. Let's look at the proof here. Okay, so let's look at this, right? I'll just start with some trivialities, but they're important. So let's let our omega, okay, possess, let's say a finite number of points. Okay, then let's define the number of elements in A given B. Okay, as the number of elements okay, as the number of elements X. Okay, X in A, such that X also belongs to the reduced sample space B. Okay, then by that definition, it means that the number of elements being in A given B is essentially the number of elements in A intersection B. All right, good. Now, let's suppose. So yeah, we're just making some theoretical arguments to be able to establish the proof. All right, so now let's suppose we want to represent our various components in generality. So the number of elements in my sample space, that's just my sample size. All right, so let me just represent this by n. Keep in mind that this n here is different from this n here, right? This n is n as a sample size. This n here is simply n as, let's say, a number, okay? A number of something. So this is just a count or a counter. So the size of our sample space is n. Let's also suppose that the number of elements in B is m. Also, let's call the number of elements in A given B as K. We're making these substitutions just so that the derivation is more, simplified. So we recall that by the very definition that we made, the number of elements in A given B is the number of elements in A intersection B. So the number of elements in A given B is equal to K. Then it means that the number of elements in A intersection B is also equal to K. All right. Then based on the above, what is the probability of B happening, right? So then the probability of B is given by number of elements in B over number of elements in omega, okay, by classical definition. And this is M over N. Also, or additionally, okay, additionally, let's find the probability, and just keep this in mind. Whenever you're working on proofs, right, you should be able to see the end from where you start and be very intentional about certain choices that you're making. So I am proving the case, this first case here, right? So it means that I need to I'm trying to find the probability of B, which I've just done. And the next step is to find the probability of A given B. The idea is to multiply the two components and see if that would amount to this, right? Or yes, or to find the probability of A and B and see if that would amount to their product. That's the point. So additionally, the probability of A given B, as we know it, is what is it going to be? It's what the probability of A intersection B over the probability of B, right? So from here, the probability of A given B, just looking at this, is also what? The number of elements in what A given B over the number of elements in omega. All right. And this is essentially number of elements in A given B, right? Is K. K over the number of elements in omega is what? N. So we have what? K over N. All right. So let's just proceed here. So or hence that the probability, okay, that events A and B occur simultaneously, okay, is given by probability of A intersection B. All right. And this is equal to, let's just take a look at it. This is going to be the number of elements in A, the number of elements in A intersection B, okay, over the number of elements in the sample space. So this is over just by classical definition. And look at this. This is actually equal to K over what? N, right? Good. And this K over N can be written as M over N multiplying K over M. All right, because the M's cancel each other. So K over N is the same as taking M over N and multiplying by K over M. Okay. So here, let me just do a quick correction. So keep in mind that because this is a conditional probability, right? The number of elements, the conditional probability of A given B, right? It's going to be the number of elements in A given B over the number of elements in B, okay? Because that's the reference event. All right, so let me just do a quick. All right, because of the reference event. So this is going to be K over M. Keep in mind, if it had just been a marginal probability, okay, like a single case probability, like the probability of B, classically, it would be the number of elements in B over the number of elements in the sample space. But when you have a conditional probability, right, it is the number of elements in the set A given B divided by the number of elements in B. All right, so that gives us K over M. So K over N is the same as M over N multiplying K over M. And this is equal to, what is M over N? It's something we've computed before. M over N is what? The probability of B. And K over M is also the probability of A given B. Okay, so we've proved that indeed the probability of the joint occurrence of two events, A, B, is the product of the, I mean, depending on how you want to go about it, it's basically the product of the marginal probability and the conditional probability. And you need to choose it very well in such a way that the in this case, if your reference event is B, then you're multiplying it by the probability of the marginal B. If your reference event is A, then it means that you're multiplying by the probability of the marginal A. So you want to, I encourage you to take a look at this. I think we have proved for the case of the second case, right? Let me just correct, just to double check. Yes, so probability of B multiplying probability of A. So we have done the first part. You can also do the second part, okay, by following a similar argument. So let's look at a follow-up to this, a corollary. So let's take a look at the follow-up, okay, the corollary. So this is theorem star star. So let me call this corollary. All right. So now we're looking at multiple events, let's say 3 events, right? So the probability of the simultaneous, okay, or joint occurrence of 3 events, A, B, and C, okay, is, so we want this time around the probability that 3 events occur jointly. So the probability of A intersection B intersection C. All right. So this would be the probability of A multiplying the probability of B given A multiplying the probability of C giving A intersection B. Okay, of course, where the probability of A is not 0 and probability of A intersection B is also not 0. Let's look at a quick proof. Right. So we know that recall that by the associative law, okay, by the associative law, I could write this A intersection B intersection C. I can just simply write it this way. Okay, so I can just group it. Right. So I'm just going to take the probability of both sides. So this implies that the probability of A is given by the probability of A intersection B intersection C. Okay, and this is the same as the probability of A intersection B. All right, intersection, the probability of C intersection B. Right, so let's just take a look at this here. If you like, one approach is to consider A intersection B as, let's say, some D. All right, so we know that the probability of, let's say, D intersection C, okay, by this rule, the probability of D intersection D, the probability of D intersection C would be the probability of C multiplying the probability of D given C. Okay. Otherwise, you can also just, from this side, we can say that this is the same as taking the probability of A given B, the probability of A intersection B, all right, and intersecting it with so this is essentially the probability of A intersection B, okay, and from here we can just multiply that by the probability of C. Given A intersection B. All right. And we know that the probability of A intersection B is the probability of B, okay, multiplying the probability of A given B, now multiplying the probability of C given A intersection B. Okay, so there we have it. So the whole argument begins from here, right? If we let this represent, let's say, some D, then it means that we can have the probability, this right-hand side. Okay, let me use my highlighter. This right-hand side. Okay, if I want to apply this rule, the probability of A intersection B intersection C, okay, would be the same as the probability of C multiplying the probability of A intersection B intersection C. Okay, let me just do that rough work here. Right, so just think about it this way. So we have the probability right? So just a rough work here. We're talking about this, okay? So this becomes the probability, okay, of C, okay? Because we're looking at this, the probability of C multiplying the probability of A intersection B given C. Okay, that's what we're getting from this, right? So from here, it can even follow, all right? You can follow the argument through from the side if you unpack it and you apply the relevant algebra. And of course, we can also extend this to, let's say, the nth case, right? So let's just quickly do that. So I can just write it without proving. We can find a more generalized format. So another corollary, okay? So this is a generalization, okay? So corollary star, star, star. Okay, so this time around, we're not looking at just two events. We're not looking at just three events. What happens if there are several events? Okay, maybe some n events. So we can say that for any events A1, A2, up to AN. Okay, where of course the so these are events. Okay, so we're saying that given this, the probability of the AIs, the probability of the intersection of the AIs, so I moving from 1 to n, of the AIs, okay, which is equal to the probability of A1 intersection A2 intersection all the way to intersection AN. Okay, this is given by the probability of A1 multiplying the probability of A2 given A1. Okay, multiplying the probability of A3 given A1 intersection A2. All right, multiplying, so it would go all the way, if you can see the pattern, going all the way into the probability of A, let's say n minus 1, okay, given A1 intersection A2 intersection all the way up to intersection A n minus 2. And then finally multiplying this by, okay, the final term from n minus 1, we go to n, right? So an given A1 intersection A2 intersection all the way up to an minus 1. All right. So that should be basically it. So you recall that in the addition, for the addition law, we looked at the general addition law and then the special addition law. Okay, the special addition law actually can be obtained from the general addition law in the case where the events are mutually exclusive, right? The general addition law provides for the case where the events may overlap, right? So in the same way we have the general multiplication law, we also have the special multiplication law. All right. So let's take a look at the special multiplication law. Special multiplication law. Multi. Right. So theorem. So this is supposed to be theorem star, 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 I think. All right. So we need to consider two independent events. All right. Consider two events. Two events A and B. In the same sample space. I mean, this is even trivial. So let's talk about in the main omega, in the same omega. In the same omega, right? So consider two independent events. And we will talk about independence as we move ahead. Okay, I think we've actually done that, if I recall, but you know, we'll double check. So consider two independent events, okay, A and B in the same sample space. Then it holds that the probability of their intersection is essentially the probability so in fact independence is defined as this, right? Two events are independent if the probability of their intersection is equal to the product of their respective probabilities. And the two events become dependent, right, if this equality does not hold. So if the left-hand side and the right-hand side are, you know, take on different values. We can talk about mutual independence or dependence. And we can also talk about pairwise dependence or independence, right? When you talk about pairwise, it means that you're considering several events, but you're considering them in pairs or two in turns or alternating. Whereas the mutual, I mean, yes, so for mutual, you're considering all the events at the get-go. All right. So there is a corollary here. And this can be proven, right? So as a corollary, so okay, so we can say that we can generalize it and say that for a set of n independent events, AI, okay, I is equal to one, two to n, right? Then the probability of the adjoint occurrence is the same as the probability of their individual, I mean, it's the same as the product of their individual probabilities. Okay. So for a set of n independent events, AI, okay, so what this means is that we have some events, A1, A2, A3, all the way, right? So then it means that the probability, okay, of A1 intersection A2 intersection all the way to intersection AN is given by the probability of A1 multiplying probability of A2 multiplying all the way to the probability of AN. Okay. So thus, I just want to write this in shorthand form. So equivalently, okay, I can rewrite this whole expression as the probability of this big intersection, okay, of AIs. I is equal to 1 to n. Okay. And that's equal to the product of the AI. So just as we have sigma, we also have the product. So AI, all right, and I'm multiplying. I is equal to 1, okay, all the way to n. So the two statements are the same. All right. So those are some of the critical issues that need to be considered in that regard. All right. So just a quick recap. We have been talking about the, still on issues regarding some basic but important laws and theorems of probability. And we started by considering what conditionality means and the various cases. And depending on the relationship between A and B, the conditional probability of A given B will either be 0 or 1, or basically the ratio of the probability of A to the probability of B. Right? We've established certain theorems, by proving that if you have an equiprobable sample space with events A and B, then we can write the probability of A given B in this form, right? And we've touched on the general multiplication law and the respective proofs. We've also considered certain corollaries. What if we don't have just two events, but we have a lot more than two events, right? And we have even further extended, okay, beyond two events to three events. That's the first corollary. And now we've looked at what if we have n events? And then we've talked about also the special case, the special multiplication law, right? And this is the statement. So in the next session, we would leverage on all of these, and we would consider total probability, the idea of total probability, and that would lead us into the Bayes theorem, right? And then we could proceed from there. So I'm looking forward to that particular session where all of these things that we've considered so far becomes very, very much applicable. All right. So thank you very much for your time.